Standard Ethernet. The original Ethernet was created in 1976 at Xerox Palo Alto Research Center, in short, PARC. Since then, it has gone through 4 generations. Standard Ethernet, Fast Ethernet, which is 100 Mbps, Gigabit Ethernet, which is 1 Gbps, and 10 Gigabit Ethernet, it is the speed of 10 Gbps. You can see these all in figure 3. You can see that Ethernet evolution through 4 generations. First one, Standard Ethernet, which is having the speed up to 10 Mbps. Second one, Fast Ethernet. It is having 100 Mbps speed. Third one, Gigabit Ethernet. It is having the speed of 1 Gbps. Last one, 10 Gigabit Ethernet. It is having the speed of 10 Gbps. We briefly discuss all these generations in this chapter, but mainly we discuss Standard Ethernet and Gigabit Ethernet in this class. Let us see in this MAC sublayer. See, in Standard Ethernet, the MAC sublayer governs the operation of the access method. It also frames data received from the upper layer and passes them to the physical layer. Let us see frame format. The Ethernet frame contains 7 fields: preamble, SFD, DA, SA, length or type of protocol data unit, and upper layer data and CRC. Ethernet does not provide any mechanism for acknowledging received frames, making it what is known as an unreliable medium. Acknowledgement must be implemented at the higher layers. The format of the MAC frame is shown in figure 4. You can observe that. Let us see first one, preamble. The first field of the 802.3 frame contains 7 bytes, means 56 bits, of alternating zeros and ones that alerts the receiving system to the coming frame and enables it to synchronize its input timing. The pattern provides only an alert and a timing pulse. The 56-bit pattern allows the stations to miss some bits at the beginning of the frame. The preamble is actually added at the physical layer and is not a part of the frame. Second one, start frame delimiter. A second field signals the beginning of the frame. The SFD warns the station or stations that this is the last chance for synchronization. The last 2 bits is a double one and alerts the receiver that the next field is the destination address. See, I said second field. The second field, you just assume that 1 byte. That 1 byte, you just assume 10101011. In this, the last 2 bits is 11 and alert the receiver that the next field is the destination address. Next one, destination address, DA. The DA field is 6 bytes and contains the physical address of the destination station or stations to receive the packet. We will discuss addressing shortly about this. Next one, source address, SA. The SA field is also 6 bytes and contains the physical address of the sender of the packet. Next one, length or type. This field is defined as a type field or length field. The original Ethernet used this field as this field is defined as a type field or length field. The original Ethernet used this field as the type field to define the upper layer protocol using the MAC frame. The IEEE standard used it as the length field to determine. The IEEE standard used it as the length field to define the number of bytes in the data field. These both uses are common today. Length or type field, these both are using common today. Next field, data and padding. This field carries data encapsulated from the upper layer protocols. It is a minimum of 46 and a maximum of 1500 bytes. Last field is CRC. CRC means cyclic redundancy check. Contains error detection information. In this case, a CRC32 that we will see in the next chapter. Let us see frame length. Ethernet has imposed restrictions on both the minimum and maximum lengths of a frame. You can see in the figure 5 that is on the screen. The maximum length restriction is required for the correct operation of CSMA CD. An Ethernet frame needs to have a minimum length of 512 bits or 64 bytes. Part of this length is the header and the trailer. If we count 18 bytes of header and trailer, in this 6 bytes of source address, 6 bytes of destination address, 2 bytes of length or type and 4 bytes of CRC. Then the minimum length of data from the upper layer is 46 bytes. How it will come means 64 bits minus 18 bits, then you will get 46 bytes. If the upper layer packet is less than 46 bytes, padding is added to make up the difference. The standard defines the maximum length of a frame without preamble and SFD field as 1518 bytes. If we subtract the 18 bytes of header and trailer, the maximum length of the payload is 1500 bytes. The maximum length restriction has two historical reasons. First, memory was very expensive when Ethernet was designed. A maximum length restriction helped to reduce the size of the buffer. Second, the maximum length restriction prevents one station from monopolizing the shared medium, blocking other stations that have data to send. See, in this you must remember one thing. The frame length, minimum frame length is 64 bytes. In the form of bits, 512 bits. The maximum frame length is 1518 bytes. In the form of bits, 12,144 bits. You just look at the figure 6. On this, you can observe the addressing. Each station on the Ethernet network, such as a PC or workstation or printer, has its own network interface card, which is NIC. The NIC fits inside the station and provides the station with a 6-byte physical address. You can see on figure 6 on the screen, the Ethernet address is 6 bytes. In the form of bits, 48 bits. Normally written in hexadecimal notation, which a colon between the bytes. See, the example of the Ethernet address in hexadecimal notation 06:01:01:02:01:2C:4B. See, 6 bytes, how it has divided. 6 bytes equal to 12 hexadecimal digits equal to 48 bits. So, like that it will be divided. See, unicast, multicast and broadcast addresses. Unicast and multicast and broadcast addresses. A source address is always a unicast address. The frame comes from only one station. The destination address, however, can be unicast and multicast or broadcast. Just look at figure 7. It shows how to distinguish a unicast address from a multicast address. If the least significant bit of the first byte in a destination address is 0, the address is unicast. Otherwise, it is multicast. The least significant bit of the first byte defines the type of address. If the bit is 0, the address is unicast. Otherwise, it is multicast. A unicast destination address defines only one recipient. The relationship between the sender and the receiver is 1 to 1. A multicast destination address defines a group of addresses. The relationship between the sender and the receivers is 1 to many. The broadcast address is a special case of multicast address. The recipients are all the stations on the LAN. A broadcast destination address is 48 ones. The broadcast destination address is a special case of the multicast address in which all bits are ones. Let us see one example in this. Define the type of the following destination addresses: 4A:10:10:21:10:1A. B 47:20:1B:2G:0:8:W. C FF::FF::FF::FF::FF::FF. See, solution. In the among these three, which one is unicast, which one is multicast? How to identify? You can observe from that solution. To find the type of the address, we need to look at the second hexadecimal digit from the left. If it is even, the address is unicast. If it is odd, the address is multicast. If all digits are F's, the address is broadcast. Therefore, we have the following. A. This is unicast address because A in binary is 1010, which is even. Second one, B. This is a multicast address because 7 in binary is 0111, which is add. C. Third one. This is a broadcast address because all digits are F's. Let us see another one. Example 2. Show how the address 47:20:1B:2E:08:00 is sent out online. Solution is the address is sent left to right, byte by byte. For each byte, it is sent right to left, bit by bit, as shown below. 11100010, 00000100, 110110000, 0110100, 0001000, 0111011. Okay. Next, physical layer. Standard Ethernet defines several physical layer implementations. 4 of the most common are shown in figure 8. You can see that. The first one, 10 base 5, the standard Ethernet common implementation, you can see on the screen. The first one 10 base 5, second one 10 base 2, third one 10 base T, fourth one 10 base F. See, the 10 base 5 we will use bus and thick coaxial cables. 10 base 2 you will use bus and thin coaxial. 10 base T, it is used in star connections and UTP connections. And 10 base F, this is used for star connection and fiber optic communications. See, encoding and decoding. All standard implementations use digital signaling. Baseband at 10 Mbps. The sender data are converted to a digital signal using the Manchester scheme. At the receiver, the received signal is interpreted as Manchester and decoded into data. Manchester encoding is self-synchronous, providing a transition at each bit interval. You can look at the figure 9. It shows the encoding scheme for standard Ethernet. See, Manchester encoder, it is taking 10 Mbps data, and Manchester decoder, it is giving 10 Mbps data. See, the station, it is receiving 10 Mbps data using Manchester encoder, and station giving the data using Manchester decoded up to 10 Mbps data. See, here it is, here they are using Chester pair arc fiber optic cables. See, the first implementation is called 10 base S, thick Ethernet or thick net. The nickname derives from the size of the cable, which is roughly the size of a garden hose and too stiff to bend with your hands. 10 base S was the first Ethernet specification to use a bus topology with an external transceiver. Transceiver means transmitter or receiver, which are connected via a tap to a thick coaxial cable. You just look at figure 10, shows the schematic diagram of a 10 base 5 implementation. The transceiver is responsible for transmitting, receiving and detecting collisions. The transceiver is connected to the station via transceiver cable that provides separate paths for sending and receiving. This means that collision can only happen in the coaxial cable. The maximum length of the coaxial cable must not exceed 500 meters. Otherwise, there is excessive degradation of the signal. If a length of more than 500 meters is needed, up to 5 segments, each a maximum of 100 meters. Repeaters will be discussed in the further chapters. Let us see 10 base 2 implementation. 10 base 2, which is thin Ethernet. The second implementation is called 10 base 2 thin Ethernet or cheaper net. 10 base 2 also uses a bus topology but the cable is much thinner and more flexible. The cable can be bent to pass very close to the stations. In this case, the transceiver is normally part of the network interface card NIC, which is installed inside the station. You just look at the figure 11. It shows the schematic diagram of a 10-base-2 implementation. Note that the collision here occurs in the thin coaxial cable. The implementation is more cost effective than 10-base-S because thin coaxial cable is less expensive than thick coaxial, and the T connections are much cheaper than taps. Installation is simpler because the thin coaxial cable is very flexible. However, the length of each segment cannot exceed 185 meter, close to 200 meter, due to the high level of attenuation in thin coaxial cable. Next one, 10-base-T twisted pair Ethernet. Here you can see figure 12. It is having 10-base-T implementation. The third implementation is called 10-base-T or twisted pair Ethernet. 10-base-T uses a physical star topology. The stations are connected to a hub via two pairs of twisted cable. You can see this in figure 12. Note that two pairs of twisted cable create two paths, one for sending and one for receiving, between the station and the hub. Any collision here happens in the hub compared to 10-base-S or 10-base-2. We can see that the hub actually replaces the coaxial cable as far as the collision is concerned. The maximum length of the twisted cable here is defined as 100 meter to minimize the effect of attenuation in the twisted cable. The next one, 10-base-F fiber Ethernet. 10-base-F implementation, you can see that on the screen. Although there are several types of optical fiber 10 Mbps Ethernet, the most common is called 10-base-F. 10-base-F uses a star topology to connect stations to a hub. The stations are connected to the hub using two fiber optic cables, that is shown in figure 13. You just look at the table 1, summary of standard Ethernet implementations. See, the first column, it is showing the characteristics. The second column 10-base-5, and third one 10-base-2, fourth one 10-base-T, 10-base-F. See, media. In 10-base-5 thick coaxial cable and thin coaxial cable in 10-base-2, and 10-base-T 2 UTP and 10-base-F 2 fibers. For maximum length, in 10-base-5 500 meters, in 10-base-2 185 meters, 10-base-T 100 meters, 10-base-F 2000 meters. Last characteristics, line encoding. In 10-base-5 Manchester, 10-base-2 Manchester, 10-base-T Manchester, 10-base-F also Manchester.